Right. Last week we were still working on using sequence models. Specifically, we're using LSTM to see how we can predict a sequence. So I had a notebook I was working on, and we were already working on predicting um, a numeric sequence based on well, it was generated data, but we were able to use LSTM to predict. And I think that w went very well. The next thing was for us to predict sequence of words, right? And the sequence of words um, was a bit more complex, in terms of what you had to prepare, right? If you remember, sequence of words is words. So before you can go into doing anything with words, you would need to first of all convert them into numbers. And we were still working on how we would do that, right? Um, so we looked at embeddings, right? And then we looked at using embedding um, libraries in order to convert words into vectors. So those vectors is what we will now use as our training data in order to achieve training which we want to achieve using a sequence model. So I'm going to just take a few minutes to tidy that up. So if you remember, this is what we did. We started off with the basic experiment of generating a data set, a time series data set. And after we generated that time series data set, this is how it looks like. We actually had the data set had a sequence length of 50. So 50 items or 50 time steps in each sequence. And then we had 1,000 sequences. So basically 1,000 data sets, sequence length of 50, right? And so we trained a set of models starting from the regular feed-forward network, which we started off with to demonstrate how good or how bad it would be. Interestingly enough, the feed-forward network actually did very well, surprisingly. But that's probably because the sequence length was very low. And then we also tried to do this with the yeah, I'm going to skip this part because this was just a demo, right? So we tried to do this with a recurrent neural network, right? And well, that actually went quite well because the recurrent neural network, well, it's not a difficult problem, so it wasn't too difficult for the RNN to handle that. Then we also tried doing it with the long short-term memory, the LSTM, and we looked at the loss curves. In all cases, it did look like the feed-forward network was even better, right? And then we tried with the GRU, which is the gate recurrent unit. So yes, it's interesting, right? I was surprised myself by that outcome. But that just goes to show how good the networks are. This is a feed-forward loss. It really has a very low loss at the beginning, but it jumps around. But I'm sure it's because the sequence length is small and the data is not truly sequential, even though the data is sequential, like a sine wave, right? But a sine wave can also be easily, um, you know, it can be approximated with a neural network because a neural network is a very good function approximator. And the fact that it's a sine wave is, I think, the primary reason why the feed-forward network is able to perform so well because it basically is predicting. It's a simple um, function which a feed-forward network can easily um, predict, right? And so you even find that a feed-forward network was doing much better. So I'm going to change the data set and find something, that is more of a time series data set. And then you will see that a feed-forward network is not as good if there is, um, you know, time dependencies. But yeah, this was just an experiment for a demo. So here we use a recurrent neural network. You can see that here the sequence length is much longer, so it's taking much longer to train the model. When the sequence length was just 50, we're able to train the model pretty quick. Okay, so yeah, then we tried with the long short-term memory, the LSTM, which we consider that, the super model when you talk of sequence models that can solve everything, right? And interestingly, it doesn't even do that much better than the recurrent neural network. Again, this model is not inherently a sequence model, so it's not very complex. It's just a simple sine wave. And then we did prediction and visualization. So that was the end of this experiment. We went ahead to do a second experiment. So this time around, we were trying to train a model to do word prediction. So word prediction is a bit more difficult because you are effectively looking at previous words and then you want to guess the next word that that is in the sequence. And I think that's where we started. So of course, predicting words in a sentence requires us to handle those words correctly or properly. And to handle words correctly, we needed a natural language processing library to give us embeddings, basically. You need to convert words to numbers, but those numbers have to be meaningful, not just random numbers, right? Numbers that represent the meaning of those words. And that's what we call embeddings. And an embedding is essentially a vector representation of a word, right? And that vector can be any length, basically a list of floating point numbers. Okay, that's what a vector is. So we have two libraries which we're looking at. We have the word2vec and then we have the glove. So to get word2vec, you need to install these two libraries, GenSim and NLTK. NLTK is a natural language toolkit. And then GenSim. GenSim is the library that holds the models which word2vec uses to generate its embeddings. So after that, you also need to download these two additional plugins for NLTK, the punct and the punct tab. This will really help when you are doing tokenization. We use NLTK to do tokenization. So when we say tokenization, what is tokenization? The words need to be broken down into tokens because the embedding is done on the tokens, not on the entire word or sentence, even though modern large language models are so vast that they can actually embed an entire sentence because an entire sentence has meaning. But in these days, in those good old days when we were starting off with natural language processing, before we had the kind of computational power we have now to handle large language models, we were tokenizing words, right? And we're embedding those tokenized words. Okay, so this was a demo of it. So we have a list of a few sentences which I came up with, and then we use word tokenize to tokenize it, right? Word tokenize comes from the natural language toolkit, and this just tokenizes based on words, right? And we can now tokenize the entire list of sentences by passing each of the words as you know, in the list comprehension that we have here, right? And then each of those words will be tokenized and you have this. Then for us to use word2vec models, right, to embed these tokenized words, we need to first of all train the model, consider it training. So we create a new word2vec, instance here, a model, we pass in the entire list of sentences. So the thing with Word2Vec is that it creates what we call a vocabulary, right? So when we're talking embeddings, right, we talk about vocabulary. Vocabulary basically refers to all of the words that you want to embed. Okay. So when you do the embedding, you will pass in all the words that you want. Word2Vec is going to essentially um, create embeddings that relate the different words in that vocabulary to each other, right? You specify the size, which is the number of floating point numbers that will represent each embedding vector, right? That's the vector size. So in this case, we picked 100. So we're always going to have a vector that has a shape of 100, right? 100 elements, 100 numbers. Window size is the size of a context window. So this is how you think about context window. If I want to embed this word, how many words around it should I use to kind of influence the embedding vector that is generated from it? So if I'm looking at only this word, I will have a different embedding vector. But if I look at maybe two words around it, two to each side, or one word around it, right? One to each side, two words around it, one on each side. The difference will be affected by the words around it. If I extend it to more words around it, so in this case, I have fantastic is the word I want to embed, and I have four words around it, two on each side. The embedding vector will be also different, right? And a way to show, I'm going to demonstrate this shortly, right? Then, so that's the window size, okay? And the mean count is to ensure that there is at least always items in the window. Workers, this one is a programming thing. The more workers you have, the faster the training will happen. So basically, this is a way of parallelizing the process. Then SG is something that means skip gram, right? So skip gram means um, if you specify, this is basically how you handle grammage. I'm going to talk about that shortly. Okay, so this allows you to train Word2Vec on these tokenized sentences, right? So with this now, you can actually generate a vector, okay? And we can, for the word film, we generated a vector. For the word, yeah, so we can now look at the vector that we generated for film, you know, and you see what it looks like. Okay, it's a list of numbers, 100 um, elements in length. So this is 1, 2, 3, 4, 25. Let's do a little bit of experimentation, with um, embeddings. So let's start off by tweaking a few things. I still have the same list. I'm now going to, first of all, reduce the Windows vector size to just 10, right? So this might not be it's not going to be very expressive, but we are just using it for the purpose of, you know, demonstrating. So we now have a vector that is 10. If I if I give you the vector, these are the numbers. Now, if I rerun this training again, so take note of these numbers. I'm going to basically do another one here so we can compare the two, right? But I retrain is the same thing. I should get exactly the same set of vectors, as you can see. I get exactly the same set of vectors. But now, let's assume I reduce the window size a bit. So this means it is more isolated. Instead of looking at the context, the words around it to determine the embedding, right? I reduce this to 3. That's all I reduce. I now want to compare the embeddings I get. Okay, well, difference is not that much. Okay, so it's kind of still single. Now let's increase this a bit more. Let's increase the window size to 10. So I now have more words. So it's now going to pay more attention to the semantics, right? Well, okay, so the difference is not that much. There's a few small differences. So for example, this is 0.0335247, while this is 335,254, right? So you can now see that a few mild differences, at the tail end of these decimals, you see that there are some small differences. And this actually has an impact in the long run. Because remember, these little small changes in weights like this can change the meaning. So what this means is that the contextual meaning changes, but not too much, right? Of course, the entire meaning of the word will not change just because you have more words around it, right? But the meaning does change a little, and that is represented by these slight differences in the vectors, in the values inside the vector, right? So this is how the window size can affect the meaning of your embedding. Okay. Now, if I combine this with embedding, when you apply this with a bunch of other things, you can now see that a few things will change. Okay. Now, the other thing you see when you're using word to vec, for example, is that the you cannot you cannot use words that are not in the original vocabulary. In other words, the original list of sentences that you gave to it, it limits to that list. You cannot embed words that are not in this list. So that means if you are training a model, you need to ensure that you have your vocabulary that is large enough and contains all the possible words that you will see in your training data, both the current training data and the future training data. Okay. So um, that's what to make. We also have Glove, which I can look at later on. Now, the next thing is for you to be able to set up a model and train, you need to, the embedding allows you to convert the words into um, the numbers which you bring into your model. Okay. So how do you do that? There are many different ways of doing that. But definitely, um, let's set this back to what it was. So let's set it back to 100. We can still keep the window size at 10. Okay. So how you handle a case of how do I, so this is another thing you can do. You do what we call a similarity test, right? So fantastic. But you see that this similarity is not really similarity in the sense of similarity of meaning, but this is kind of similarity in the sense of which word has the greatest, impact to this, right? So similarity here, we might think it is in terms of the um, synonym, you know, similarity in terms of the word itself. But in the context of what was passed in here, right, you can find that the word, that kind of comes really close to fantastic is it. So in a way, it's telling you that when you talk about fantastic, fantastic is referring to movie and it's referring to it, right? So even though I don't see movie in this list, but there is it here. Okay, now for us to then set up our model, we first of all need to create what we call an embedding matrix. So an embedding matrix is basically a matrix that you use um, to define the relationships between the words, right? So if you look at this, you have all of these words, which are in the entire vocabulary, okay? So we are going to, what embedding matrix is essentially doing is, it is creating a two-dimensional matrix. It starts off by creating this word index, which is just a list of the words and their indexes or indices. in the word word to vec model. Then you now create a two-dimensional matrix. So this is a two-dimensional matrix that we just created. Okay. And the matrix has these dimensions. The first, the number of rows, which is the number of words in your vocabulary. Okay. Plus one. The plus one is there is a padding which you want to add to it as well. And then the embedding dimension, which is a number, basically it's the size of the vector, right? The vector size. So what this means effectively is that we are creating a matrix where each row is the vector that corresponds to the word in that vocabulary at that row or at that index. So this first one is zeros because this is a padding row. There's nothing there. This first is basically the embedding for the first word, which is movie in this case. So this is the embedding for movie. And then this is the embedding for the next word, ever. And so on. And it continues like that until all the embeddings are done up to the last embedding here, which is the embedding for this last word, this, right? So that's our embedding matrix. Basically, vocabulary and the embedding per vocabulary. So with this embedding matrix, you can directly create a layer called an embedding layer from PyTorch, right? You pass this embedding matrix that we just created as the weight of that embedding layer. You just pass it as a weight, okay? And that's what from pre-trained means. From pre-trained means you pass in the weights. You don't train the weights. You pass in the weights. And in this case, what we are passing in is the embeddings, right? So these embeddings will kind of act as the weight. And then we specify that there is a padding, and that padding is at index 0. So remember, the padding is used for words that are not in the vocabulary, specifically words like spaces, right? Period, full stops, anything that maybe is punctuation, for example, but it's not part of the embedding. Because when you are doing part of the vocabulary rather, when you are doing word tokenization, right? Things like punctuation, like commas, periods, full stop, and other punctuation may not be included, but those will be showing up in your stream of words. So all of those are represented by this single embedding that we call pad. So anything that is not in our vocabulary, right, we represent it with this pad. So that's why we have a padding, and then the index for that padding is 0. Then we also have false. So freeze means you can freeze the weight, which is this embedding you brought in, or you can choose not to freeze. If it's true, that means you freeze. That means as you are training the model, this model, the embedding is not going to change. It's not going to learn nuances, right, from your data. But if freeze is false, that means you are not frozen the weights. The weights can change. That means your embeddings can change. In other words, this embedding layer can learn as it is being trained along with the rest of your LSTM. So we now create the LSTM class, which is next word predictor, right? We create the embedding matrix, right? Or we already had the embedding matrix up here created. So we now create an embedding layer, basically just repeating this thing that we had here. But this time around, this one we did it outside, but here we are now doing it inside our model, right? So it's basically the same thing. And then we also create the LSTM, which is a sequence model that will now take its inputs directly from this embedding. That's why the input size is the embedding dimension, which is essentially the length of the vectors, right? And then we create a hidden size of about 128. Batch phase is always true because that's the way the data is arranged. Then the output from this LSTM, we pass it into a linear layer, okay, that has 128 and the vocabulary size. So the reason why we're using vocabulary size here is we want to predict the next word. What is the next word? And the best way to predict the next word is by going through the vocabulary and training this model on the probability that the next word is XYZ in the vocabulary. Sorry, in the vocabulary. So how we do that is by we will generate and I'll show you how we generate the Y, the Y true data, right? The label or training data, you know, from this. But we looked at it a bit when we were training the sine wave model. Okay. So we did that, and then here is a forward. Um, this is a forward, um, the feed forward part, right? The forward propagation. So we just pass the text through the embedding layer. So this embedding layer is going to take that text and generate embeddings for us. Okay, that's basically what it does. Is able to do that, and then we will now pass that embedding layer, embedding output into the long short-term memory LSTM. And we'll take the three outputs. As you can see from LSTM, you have the output. This is a sequence. Then you have the hidden, which is a hidden cell state, the hidden state, and then you have the cell state, right? Then what we actually want is, because we're predicting sequence, right? We are predicting is this is what we call a kind of sequence to sequence model, right? Which I'll explain in more detail shortly. We're not trying to predict a single thing like a classification model, which we'll also look at sentiment classification using this. But we're trying to predict what is the next word, right? So it's not really a sequence to sequence per se, but more like a sequence to a probability distribution. Okay. Um, so, but we would take the full output, right, from this, but we are taking the last in the sequence. Okay, we are taking the last in the sequence. And so this output is going to have the shape of, this will be the batch, the number of items in the batch, which is 1000. This one, because we are doing -1, we are just going to take the last item in the sequence. Remember, the sequence length here could be anything. In this case, the sequence length is 100, which is the embedding dimension, the size of the embedding. But we're going to take only the last, okay? And then this refers to the basically the what comes out, the hidden size here, which is 128. So we take that, right? And that's what we put into our linear layer, okay? And our linear layer will take that and give us um, the uh, probability distribution over the entire vocabulary. Okay. So that's the outputs that we'll take. All right. So um, this is basically a repetition of this, so I'm going to skip it. That's what we have in the word index. I think I was trying to explain something with this. So let me just well, let's keep it. All right. It doesn't really do anything for me. All right. So when we first of all look at this is like a random logics, which I was trying to explain. I was trying to explain what this means. Basically, you will see that I was trying to explain the probability distribution, where I said, okay, if I generated this, right, I can plot the probability distribution here. It's actually very easy. Of the outputs. So a simple way is maybe just take a bar chart, right? Okay, so this is there already. So you just take the bar chart, which contains this, right? And yeah, this is basically the word index here. And you can see that these are the categories, right? while these are the indexes. So I can use any of them. But in this case, let me take this out because this is not really needed for that explanation. Um, let's take the word index, which is what we are actually using. So this is word index. And then logits, which is a simulated probability distribution. Okay. Okay, so why we have this difficulty is the word index has the it has a padding as well. It has a padding as well. So um, I should add a padding here. It started from 1 to 20, while our vocabulary size is 21. If we count this, it's 21 because we added the padding as well. So we can just start from 1. Okay. So yeah, this is taking a bit longer. Um, okay, vocabulary. Oh, right. Uh, okay, so this is not a list. This is just an integer. Okay, so yeah. So this is kind of what when we say probability distribution, okay, it basically means that if I were to predict, let's see how we can flip the y-axis so that we can see this um, better. Okay. Um, okay. So we can just let's do this so that it can be really the x ticks um and then log weights. Okay. Rotation. Okay. Um dot values. List. Um okay. Um right. So what I actually need is okay. All right. So this is what we are looking for. Um Really don't need all of this. Um, I'm wondering why we don't really need all of this. Okay. Well, so let's just yeah, so this is it, right? Basically the same list of items that we have, okay? And you can see we have the ticks. I wonder why it's printing out the ticks, but so you would now see that this is a probability, this is a random probability distribution. It's not a real probability distribution, but this is saying like if this is what your LSTM model is predicting, it is predicting that the one with the largest probability is most likely the next word. So in this case, waste. So this is just to show you what probability distribution, looks like. Now, I was also trying to show you how glove works, but we will um so the benefit of glove is that you can download the entire set of embeddings, right? And it has a lot of different ones, but you can download this entire set of embeddings and you can use it. So anyway, while this is downloading, we will go ahead and train our model, right, with this. So let me just pull together a training loop quickly. So we have epochs. Um, by the way, the X and Y data that we are going to use, we will have to do a bit of adjustment, um, which I mentioned before. So let's look at the feature engineering that we need to do. Learning rate. We can use stochastic gradient descent. We can use you can use Adam. Perhaps we'll use Adam with a learning rate of 0.001. Um, criteria, we'll use cross entropy because this is a probability distribution. It's not a, we are trying to predict which of the words. So a probability distribution, you always use a cross entropy. Um, optimizer, we will use um, Adam, right? So we use Adam and we'll go with default. The rest of it is default. Okay. I'm not going to do any other fancy stuff because of the time constraint. Yeah, so the training loop, we will we can do early stopping as well, but let's just do yeah. So we will start um okay, so we will have to pass the sentences, we'll tokenize the sentences and we'll pass into so for each of these, right? Each of these sentences which we have in this list, we are going to basically generate, we'll tokenize and we'll pass it in. So that's how we will do our training. Oh, okay. Yes. Yes. So I think I mixed up the name of the models. So let's change the word to vec name to embedding model. So it's embedding model. So we do not confuse the embedding model with the actual model we are training. Okay. Yeah, embedding. So let's rerun this. Everything else is the same. Vector is the same. This is the same. Word index. This we will use embedding model here. Okay. Um, we create the embedding matrix here. Embedding layer, then the next word predictor. So the actual model we will now train is the um the next word predictor model. Okay. And we pass in. So remember the embedding matrix is passed in as um a property when you are initializing it. Okay. So we start with that. Um yeah. So we can tweak all of the other things, right? Okay, so let's look at um let's look at the forward again. Okay. So let's try a few things, just running a forward pass before I go into training so that I am sure of what my model is doing. So I could take model, let's just do a forward pass, and then we are going to pass in the let's pass in let's take one of them now because it's an embedding layer. We we don't need to do any embedding. It's already we just pass in the tokenized values. The embedding layer is going to handle the embedding for us. So let's so the what we have is sentences. So I can pass in sentences 0 just to get the first one and see what it looks like. And let's see what output we get. Um, okay. Um, so we will embed. We have a word index. So the word index allows us to instead of having to rerun embedding, right? We can just look up. So this is the essence of having this word index. So we will have to take each word right? And basically run embedding to it. So so the first thing is take the words, convert the words into their indexes, right? Then take the indexes and extract the embeddings. So we already have the embedding, we have the word index here, which is what we use. And then we also have the embedding matrix. So let me see if I can explain that. So first of all, we start off with sentences zero. So sentences, or rather, let's just say sentences. These are all the sentences that we want to do the these are all the sentences that we want to pass into it and just do a forward propagation. Take note that in this case, there's no training yet. All we have is embedding, right? In the embedding layer. Now, we take this, right? And we do the first is to convert each of these words into their corresponding index, right? And to find their corresponding index, you we will have to run um there are a bunch of ways you can do this with touch, right? Let me just use a simpler method. Um so for let's just do this simple. For sentence in sentences, okay. Um you can now do for token in I think I already had a tokenized version already. Um Rather than using the okay, I already have tokenized sentences. So I don't need to re-tokenize again because that's just going to slow things down. So for sentence in tokenized sentences, so what we have are the tokens. Okay, then we can then do something like funny enough, we could put all of this in a list comprehension. But yeah, let's do that in a list comprehension. It's not very efficient, but for the sake of illustration. So this is input. Input, the input is going to be first list. Um, you will have another list in there, which is going to be word index. Yes, the word index is, remember the word index is a map, kind of reverse lookup table that allows you to, from the word itself, you can get the index number. So we will do that here. So word index, okay, word for word um in sentence, right? Where the sentence is now the tokenized sentences, right? Or sentence into tokenized sentences. So if we now print input, this is what you get. So let's compare input with the original sentences. Sentences, not tokenized. So you see that the sentences, you have this movie was fantastic. I loved it. So this, if you look at the index for this, right? Okay, in order not to scroll up too much, let me also print the word index, right? The word index so we can see it, right? Let me even see if I can make it flat. Right, so this is what I'm looking for. So if you look at this word index, okay, this, if you look at the position of this, you will see that this is 20, index 20. So you have 20 here. So essentially you map this to 20. movie is position 1, so movie is mapped to 1, right? Was is position um 19, so it's mapped to 19. So we just continue like that. That's what this bit of code does. Basically, it takes all these sentences, they tokenize one anyway because it's already been tokenized, and then it maps it to give you the indexes, right? So you now have these indexes, and then each of these indexes, remember, also allows you to map into the embedding vectors because the embedding matrix has the indexes. Okay. It has the indexes, and for each of the index, it has an embedding. So what we will now do is to take that um, and use, basically you pass it into the embedding matrix, sorry, into the embedding layer, right? When I now pass this into, so let me use the embedding layer we already created, right? That's the benefit of the embedding matrix, right? Which you use to create the embedding layer. So remember, I have an embedding layer here. So I'm just going to use this embedding layer directly, right? When I pass this input into the embedding layer, I now get embeddings from it. I just pass input into it. So the input is just an index of the embeddings, right? Uh, the index of the embeddings. That's all. We converted the words into indices. And then we pass these indices into the embedding layer, which we have created using PyTorch's, embedding layer, um, you know, um, they've given us this embedding layer which handles all of that. And we had passed in the embedding matrix, which is what it uses to do the looking up. So when I now run this, okay, we'll now see the actual embeddings coming out. All right, so there's something I missed out. Yes, I've created the input, but I need to make this into a tensor. So I will do torch a tensor and float. So this is basically to convert this into a touch tensor. I cannot just pass a list of numbers into it. This is what this does, basically. Um, right. So here is another problem. I have a tensor that let's just take a single one because uh, since I am putting all of them, touch is actually expecting all of this to be the same length. I cannot convert all of this into the same length into different length in touch as a touch tensor. So we will handle that by using padding later on. So for now, in order to further simplify things, I am only going to handle a single input. So let's just go with input that. So when I do this, so the first thing you notice, I have a tensor, right, that has this length. Um, Okay, so it seems like Torch actually doesn't want a float tensor when you are using it as an embedding input. It actually wants um, an int tensor. So we can make it an integer tensor or a long tensor, an int tensor or a long tensor. So yeah, so let's make it an int tensor. Um, I could have as well done this, but I think it's still going to make this into a float tensor. Okay, so I now have the embedding. So you can see that we actually have embeddings here that match this. And to prove it, if you check here, the first element, the first index here is 20. I can go to my embeddings matrix, right? First of all, 20 is the last one, which is this. I can go to here and I can check, and you will see that this is 0.0056267, right? Which is 5.6267 raised to power minus 3, right? And I think that's what touch is giving me here, 5.6267 raised to power minus 3. So basically, what touch has given me is the embedding that corresponds to those indexes. So I pass that. So this is how I get my embeddings. Now, I can then take this and pass it into the model, right? So I don't remember I have an embedding um, layer already in here. So if I want to do a feed forward on my on this model, I just pass this embedding that sorry, not the embedding, but the indexes, right? I just pass the indexes directly in. So I can do something like y pred equals model, right? So this would be what the prediction would be, right? Okay, so I have to debug this, and I suspected we'll have a problem here. And the reason why we have the problem here is that the if you look at this model, we have an output. The shape is going to be 1 and let's let me show you how the shape looks like. So we have a shape of output. It doesn't match the shape of the next layer, right? So that's where the problem is. It doesn't match the output. It doesn't match the shape of the next linear layer. So we need to match those shapes. If I run this now, yeah, so I still see the problem, but okay, it doesn't look like. Yeah, I need to update my model to the latest version, this one, before I now run this. Okay. Um, right. Oh, okay. So I have a tensor. The dimension of what is coming out from the LSTM is only, let's check the actual dimension. So I think I made some assumptions here, which I will correct. Um, let's look at this. I made some assumptions, so let's just look at the shape of this output. As a matter of fact, I'll have the shape of all three. So the output shape from an LSTM is going to be always batch, sequence length, and the third shape should be the shape of this. So I think of course, I was just accepting stuff from suggestions from our AI. So we have to debug it. Okay, so the size of the output is 7 and 128. Um, the size of hidden is 1 and 128. And the size of the cell state is 1 and 128. So the way we will interpret this is the batch dimension, there is no batch dimension. I think that is the issue because my input shape, I did not include a batch dimension. I should have reshaped it to include a batch dimension. So if you look at, let's fix this input, right, by converting it directly here into a touch tensor. So I don't have to do it in too many places. Right. Yeah, okay, so I'll have difficulty here because I need to pad this. We'll talk about padding later on. we need to pad all of them to have the same length. Okay. Okay. So let's do this, right? What I wanted to do was to take this input. Okay, so let's just make it input one equals torch dot int tensor um input 0. Okay. Then if you look at the shape, there's no batch dimension in the shape. So you can see the size is just 7. And that's why the output is also 7, matching the sequence length, right? 7 to 128, right? 7 to 128. Ideally, I should reshape this so that it has a batch dimension, and that would have solved the problem. So we could reshape, reshape. So reshape it to -1, comma, um, yeah, this we will still keep, let's say 7, okay? That's not the perfect way of doing it, but whatever. Now, this 7 corresponds to the length of the input. In this case, 7 indexes, 1, 2, 3, 4, 5, 6, 7. Right. So I could have basically said input 1, sorry, input 0 dot shape, right, 0. So that will still work. Oh, sorry. This is not yet a torch tensor, so we'll just use a length. Okay. So that gives me this. Now, if I use this, right, it is going to give me the right, what I expect, a three-dimensional thing, because I now have a batch dimension. So the issue was I didn't have a batch dimension. All right. So with that, you can see that it works in the sense that um, I am now taking the last entry in this, and that's what I am using to feed into the this feed forward fully connected layer, the linear layer, which has 128 inputs. And that 128 basically means the 128 features, right? So it's actually going to squeeze it and feed it in. So remember what we are getting in between is 1728, but we are taking only the last of these 7, right? This is the output, which contains another sequence, except that it now has a third feature dimension. This is the hidden state, and this is the cell state. So, but you could decide to take any of this and pass it as into the next layer, depending on how. So these are some of the choices you have to make depending on the kind of problem you're solving. But most cases in a sequence to sequence model, you really want to take the output, which has the entire sequence. But in this case, I have to take the last of these 7 sequences, the last output from it, and I feed it in. And what I get back is um, a single output that is embedded. You see that this is embedded. It has 1, 2, 3, 4, 5, 6, 7. Okay, sorry, this is not an embedding. This is a probability distribution. It's going to have the same length as the vocabulary because we already defined the output of our model, right, to have the vocabulary size. So this is going to give us the probability distribution similar to what I plotted here when I was trying to kind of explain what a probability distribution is. I don't know if I have it anymore. I can't find it anymore. Um, well, seems I lost it. That was before. Okay, this is it, right? So we can now plot this, right, probability distribution as well. Okay, I could use this to plot the output from our model. Okay, and what we are plotting is the logits. The logits is Y-prate basically. It's Y-prate we are calling the logits, which is the probability distribution. So we normally call the probability distribution the logits. And you will now see, um, yeah, we should do the no um, grad numpy so that we don't plot um, um, we need to detach. I can't remember that word. Is it detach? Yeah, we need to detach so that there won't be any gradient. Um, numpy. Okay, reshape, squeeze. So we squeeze. Um, squeeze, detach. I have to do this step by step. Okay, so why bread? All right, so I didn't actually squeeze it. Um, okay, maybe we'll take a view and or reshape to just um this. Okay, so that works. Reshape, or we reshape after the numpy, so that's better. Detach numpy. Let's see what that looks like. Detached numpy is still going to be a two-dimensional thing, so we can squeeze or flatten into one-dimensional, and that should work now. Um, objects can be broadcast. Right. Okay, so we still have this one that starts off with a zero, so this is the problem. All right, so I start off with, because I've not trained this model, you can see that I start off with all of them being very similar. The probability distribution is basically telling me that this whole thing, right, is thinking they're all equal in terms of um, the numbers are really close, right? 0.05, 0.02. Even though I'm a bit surprised, maybe I'm doing something wrong here because I'm getting all of them being 0.05 something. So it's entirely possible that, let's see what this is giving me. Oh yeah. Yeah, so this is not correct. This is not correct. I did the wrong thing. One. Yeah, that was a typo. Okay, so it should be this. Okay, right. So, yeah, and interestingly, we have negative probabilities as well, which doesn't really make sense. So, you would normally have to pass this through a softmax, right? But then we can train this model this way, and we can live with it. We can go with the logics, or we can um do this um with the softmax. Typically, you should use a softmax if you are trying to predict probabilities. So let me update this to add a softmax. Um, yes. So um, we will now pass it through a softmax. That's going to give us a cleaner. That's the essence of softmax. What softmax does is that you see all of these negative and so on numbers, it will kind of give you a probability distribution that adds up to zero. So we'll see what that looks like now. Remember, this model is not trained yet. I'm just kind of experimenting with this model in order for us to really understand how to get what we want out of it. So let me go back a bit and create this model again. Then I will now run it um, by running this here. So I now have values. You see that I don't have any negative values anymore. I don't need to do all of this stuff that I was just trying out to figure out how to clean up the thing so that it will work. So this was just me trying to figure things out. Um, then we plot it. So when we plot it, you now see a probability distribution. Again, because this is not a trained model, you can see that it doesn't really show much difference between one word and the next in terms of what should be the next word. Okay. So um, we go from 0 to 19 and text 19 this, right? You can see this has a very low, well, not very low, but you can see the values. You can compare the values what we have here. 0 point, everything is ranging around 0 0.047, 0 0.05 after soft maxing everything. Okay, so that's kind of doing exploratory on our stuff. Now, the next thing we have to do is we will now train, right, on just on just these few words, right? We could train on just one word and it will actually be able to maybe predict, right? Um, but one way we can do this is um so if we want to generate the training data, remember, first of all, we need to pad and then we need to generate what the next word is. So yeah, we need to pad and then we need to generate what each word is going to be. So so the first thing we are going to do is we will first of all have to we can loop through this, right? Uh, and I'm going to show you just for explanation the simple way of doing it. Then we're going to use a PyTorch data loader later on. So the first thing is we have to think about padding, okay? And what happens is if you look at this sentence, let's start with the first sentence that we have, tokenized sentences. Let's just look at this again and analyze this. So we want to train on this simple list of sentences or list of tokens, which forms the first sentence. We can generate, this is what we would normally generate from this, right? We'll generate a list that is made up of um, okay, right. So I'm trying to figure out how to do this in a list, but let's just say training the training X data. We start out with an empty list, okay? And then we will now do a um for I in length. Let's take the first input, uh first tokenized sentence. So we take the first tokenized sentence and um tokenized sentences. So essentially what we are doing is I'm looking at the length of the entire token or the tokens in there, right? And then I will now create um yes, I'll now create a subset, right? Okay. So um we will start from um word index word. Okay, hold on. Let's just we already have the word indexes, so let's just use that directly. Even though I wanted to use these sentences, but um okay, let's use the sentences just for illustration. So I want to create a subset. So the first subset I want to create will only contain this, right? So that's going to be essentially um X, okay, for X in um nice. Okay, hold on, this should be range or for yeah, um for tokens in tokenized sentences. I don't need to do this. Um in tokens, um I, right. I think I was correct. So this is I need to think about this a bit. Range length of tokenized sentences. So want to append um X for X in tokens. I, yeah, um tokens tokenized. I um 0. I, right. So let's just let me again show you what this does. Okay, so this is what I was trying to achieve, right? Basically, you take this, okay, and you just take each token first, right? That's the first. So you're essentially creating multiple training data from this single one. And the first one is this, right? Which is just the first one. And the next one is this movie. Then the next one is this movie was, right? This movie was fantastic. So basically, that's what we have done. We have created a list of sequences, subsequences of this original one. But the interesting thing is that's a training X. Now, what is a training Y? So a training Y is what we are going to use as a prediction value. So for the training Y, we will use it to predict the ith value. Okay. So we can now print training X and training Y, and you see what that does. So this is what we are saying. When there is nothing, right, it's predicting this. When there is this, right, it's predicting movie. When it is this movie, it's predicting was. Okay. When it is this movie was, okay, it's predicting fantastic. When it is this movie was fantastic, it's predicting I, and so on. So effectively, the Y data is the next word. Now, we are not supposed to start from the first one. We really should start from, um, because we don't like, we should only start predicting when there is a this. So I'm going to tweak this a little bit, right? 0. Let's start from one, from one. Okay, so if we start from one, this will give us, okay, so starting from one, we actually missed something. Um, so we really should start from 0, but we end at the end. Okay, that doesn't give me what I want. Okay, so, right, this should be I plus 1, and I, well, that's not going to give me what I want either. So we don't want the first one because the first one is a 0 pad basically. But then maybe we can just have this and then we can remove the first, you know, elements of it. So if we remove the first elements of it, we are basically removing the first elements of each. That's another quick way of doing it. So this is now what we have. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, but remember, touch will not allow us to um touch will not allow us to convert this into a tensor directly because it is not a fixed length thing, right? So we have to pad stuff at the beginning. So to do that, one way would be to essentially create empty stuff, like put in a pad character, what we call left padding, which you can do separately. And it's easy to do that. Let me show you how to do that. So um, the pad character, or we can convert it and then we pad with zeros, which is better because we already said our padding embedding is 0. So yeah, so we can easily convert this. So this was just for demonstration. Now I'm not really going to go do this with tokenized sentences. Rather, I'm going to use the actual input, which has already been um, translated to index. So I can just use the inputs directly. And that will now give me the actual numbers instead of this. So you can see it gives me the numbers, right? And but we need to pad. So we can left pad short X values, right? So to left pad, um, well, they have this pad sequence thing that we can do, right? Um, well, let's still do it manually. So to left pad, I would do something like this. Um, you would you could just do Um, so first of all, we would have a pad, right? So let's call this pad equals just a single list of zero. Then you can um we can do pad times. So you would have to take this pad. It should be as long as the gap. Okay, so length of training x I, right? Minus, so that's going to be um the longest in this list is the last one. So you could also do minus length of training x minus one. So this is the last one. So effectively what we are doing is we are saying the amount of zero padding I'm going to give to anyone for all of them in training X, right? For all of them, the amount of padding I'm going to give, right, is going to be oh, this should be reversed. The length of the longest one, which the last one is always the longest one, right? Minus the length of the current one I'm padding. So that calculates the length of the padding, right? And you multiply that by the pad, and then you pad it to the left. So that's how you do the padding. So with this now, I can actually check this again. And I can check this again. And you now see that I have the padding in place because I've done a padding thing. So everything is now the same sequence length. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, and you have the correct indexes. And then this is the Y values, which is the index of what should come after this. So essentially, we are saying when we have 20, right, we should predict 1. When we have 1, we should predict 19. When we have 19, we should predict 18. When we have 18, we should predict 17. When we have 17, we should predict 16. When we have 16, we should predict 15, right? So that now gives us our training X value. We can now pass this into our um, model and create our training loop. So this is where we can now do our training loop for epoch in epochs. You start, um, we don't need to do this anymore. We can just do a torch. Yes, so let's just do torch training X, right? So we just convert it to torch tensors, int tensors. For the Y, yes, for the Y, we would also do a lookup. So for the Y, we need to come up with a one hot. We need to one hot the Y, right? Because the Y is saying this is the index, but this index, we will now do a one hot encoding. Okay. So the best thing is to do a one hot encoding and then we use that. So convert Y into a one hot encoding. Okay. So that will be that. So you use touches one hot and then you specify the number of classes. The number of classes is the vocabulary size. So this is correct, right? So if we do this, by the way, right, let me just show you what you get by doing a one hot encoding on the Y values. Um, right. Okay, so I did not do the torch thing yet. So let me just do the touch thing. This is just for us to see what the one hot encoding looks like. So we have to convert it to a long tensor. So we get this one hot encoding, which basically is saying for the first one, remember the first y, the value is 1, right? So we get 1 here. For the second y, the value is 19, so we get it at position 19. So interestingly, it's counting from this other end, which is quite surprising. 18, right? You have this 17, 16, 15, and so on. So I'm surprised at this. Oh yeah, okay, that's I think I wasn't the first one is 0 actually. The first one is a 0 position, which is a padding. So that's why it's down here. This is a 0 index. And this is the 20, this is a 20th position, right? And sorry, this is 0 index. This is 1. This is 0 index. This is 1. And this is 19, 18, 17, 16, 15. So we have to be able to understand what we are getting so that we know that we did not make a mistake in our code, right? So yeah, this is 19, 18. This is 20 actually. So this is actually 20. I don't know why 20 is in this position, right? Um Yeah, but we have 20 in this position. Oh, that's correct because 20 is actually in the original best position, which we had. We actually had 20 there. So this is 20, then 1, then 19, 18, 17, 16, 15. So the one hot encoding is okay, is correct. So we do the one hot encoding and then we can now train our model based on all of the other parameters that we had. I'm going to bring all of this down because we've done a lot of things in between. So, um, yeah, let's do this. Um, all right. Right. Um, so we have a model, we have epoch learning rate and all of this. Okay. So we will now start our training. So we always start training by model.train, and then we do the prediction, model dot we'll just do the prediction. Y pred equals model. We pass in the X values, training X. We get our loss criterion and we do optimizer zero gal. We do a loss backward. We do a optimizer step and we can calculate loss. We can store the losses. Let's do that. Losses. I'm not doing validation for now. But we can do that later. So losses dot append. Okay, we will now append the latest loss item. Okay, and we have trained this model just on one sentence, by the way. We trained this model just on one sentence. And we use 1,000 epochs, learning rate, Adam, and all of this. So we can also decide to print the losses. If epoch is this, we can just print the losses as well. And that's it, right? A simple training loop. Um, oh yeah, I already had this error, which I forgot to fix here. So you cannot use an int tensor for one hot. So we'll have to change it to a long tensor. We use the int tensor for the training, which is an index. Okay, it looks like I have another challenge. Um, um, okay, it does look like let's see. I hope I didn't change something. Let's do this again. All right. Then we pad. Okay. Uh, okay. I think we just put this in here. So I'm surprised that we are having this problem. Okay. We can convert the one hot to float. We can convert the one hot to float. And so now it's telling me that zero dimensional, one dimensional target test expected, multi-target not supported. Um, right. Let's see what this actually gives me. I have to start again. Okay. So now we are training and I think I ended up printing stuff I shouldn't have printed. So let me take it off and start again. So again, yeah, there's a bit of fragility in this code, mainly because, yeah, but right. Um, okay, this is from the output. Yeah, so we're having loss here. So this is in the model itself where I was doing a bit of um let's see where I define the model. I need to remove that print statement. Okay. So I have to start again. Right. Um, let's come back here. So we start loading our data again. We have that, the indexes, we have padded it now. Um, we now have this, and we now have training. Okay, so finally we see loss. Loss is not dropping a lot. Okay, so we will adjust that shortly, but let's look at the um let's see how our loss looks like. So just plotting the losses. Okay, so it goes and it flattens out. Now, one thing you get when you have a situation like this where your model kind of flattens out like this, you may be asking, like, okay, do I have enough data? This is more of underfitting. You don't have your model is not large enough actually, right? The model is not large enough to predict. And yes, we really are trying to do use a single LSTM to do something that is really you know challenging, right? But then I'm trying to use this to explain a few things when it comes to natural language processing and so on. Now, we can let's do another round of trying to predict. Now that we've trained it a little bit, right? The loss has only dropped from 3.04 to 2.12. So, okay, it's learned a little, but it's not good enough for anything. But let's just look at um let's do yeah, let's do the um prediction. So we can just give it input one again, input zero. Okay, but I'm not going to give it the entire thing. I'm going to give it maybe like the first five words. There are seven words there, so I'm going to give it the first from um yeah, the first five words maybe. And then yeah, let it predict the distribution. Okay, I need to turn this into a tensor. So touch that tensor. I always forget that this should be an int tensor. Basically, which is a tensor of the indexes. Too many indices for tensor of dimension two. Okay, let me be sure. Okay, well, this is correct. This is what I did before, and it did not. So let's see if I missed something. Input one has a shape. Oh, okay. So, yeah, I need to reshape it. I forgot that I did a reshape here, so I need to reshape it. So I'm sure a question a lot of you will be asking is this what I have to remember to do? I have to remember to do all of these things. Um, yeah, this has a length of five. So you find that when you are doing sequence models, the biggest challenge you will have will be sequence lengths on equal, uneven sequence lengths. But the good news is that Touch has ways to handle all of this. Okay, so we have this prediction. I'm now going to take this prediction and I'll print it using this same kind of thing. I'll print it as a graph. I'll print it in a graph so that we can see what our model has learned, right? Based on this. So this is basically the same thing. Right. So our model has actually learned and has optimized for two words, it and loved, after training. So let's check again. What were the three words that we gave? The first three words in the training data. This let me see if I can remember the actual words, which is input zero, um sentences. It's just sentences zero, right? But after the first five words, because we are asking to predict after the first five words, right? 0 to 5, which is 20, 1, 19, 18, 17. 1, 2, 3, 4, 5. So the first five words in that sentence was 1, 2, 3, 4, 5. This movie was fantastic. I loved. And well, it predicted it with a higher confidence than loved. So it loved. Maybe we didn't do something right, but at least we can see that the model has learned, to predict that particular sequence. Of course, if you throw in other stuff, it may not be able to do. So now the question is, how do we train on a larger scale, right? More words and more stuff. How do we handle all of these little um, technicalities that we have just been dealing with? Things like the sentence length, unequal sentence length. And remember, in this case, we're just training on just one single sentence, which we created a lot of different um, basically sequences, starting from the first word up to the last word and all of that. How do we handle this kind of issue, right? Does PyTorch provide um, does PyTorch provide all of this? So we'll see how I'm going to start a new notebook and just run this, you know, with um, PyTorch using PyTorch helpers. So by the way, one thing we did add a softmax, but we shouldn't we shouldn't add a softmax. I think I added a softmax because I wanted to see the distribution, how it looks like, right, with a softmax. But when you are training the model, it is not advised to don't put in a softmax. The main reason why is because the cross entropy loss already is going to softmax your output before it does the cross entropy loss. So it's better, and that's something that kind of happens in training. So if you are doing inference, you are going to have to train with the logits. So the logits are these ones that have not been softmaxed yet, right? But when it's softmax, it kind of gives you the probability distribution. Okay. So when you are training, don't use softmax in the model. You can train with the logits, right? And then when you want to do inference, you can append softmax at the end if you still want to do your probability distribution. That's kind of the thing. So let's try again this time around without using softmax. And I want to see if my model is able to do a better job. So again, um, let's let's see. I'm going to start this model. So I'm going to bring the model up here and predict without um predict. Okay, so model without training it. Let's see. Um, so this one, yes. So I have this model now. Okay, I need to get all of the other stuff. Maybe I should just run everything. So let me rerun everything. And okay, so while that is running, because we don't have a lot of time, I'm basically going to start another one. And this time around, we'll just use PyTorch for the whole thing. The other thing I would like us to do, I would, if we can do it fast enough, is what we call sentiment analysis. So sentiment analysis is a classification problem, right? What we just did here is a sequence to sequence. Well, it's a prediction problem. You're not really classifying, you're trying to predict the next word. So you're trying to it's kind of classification, but it's a probability distribution, right? So you're classifying based on the vocabulary that was given. Okay. All right. So this is the first time I did this. Okay, this is just random. So I'm not oh, we're still doing this. Oh, wow, this is going to take a bit of time. So we'll come back to it. All right. So let's do this now, end to end. Okay. This time around, we'll use PyTorch to help with a whole bunch of stuff, including um sequence length and so on, so many things. So we import PyTorch, torch utils, data loader. We're going to use dataset and data loader. We're also going to use a pad sequence to pad our sequences. So all those things I did manually, right? With respect to padding sequence, right? We're still going to use the same sentence list, just to be able to compare. So this time around, we are going to create training data from each of these sentences. Okay. Now, one of the things we are going to do is that we are going to actually reserve 2 slots in our sequence for padding, right? So we'll use 0 for pad, which means pad is space characters and so on. We'll use 1 for unknown, right? For characters we don't know. So this is still loading. So that's what we'll do there. Then we're going to create a tokenize function that will help us to tokenize. Now, in this case, we tokenize using basically we make our own simple tokenizer, right? That just tokenizes based on sentence boundaries, species, right? The other one I use word to vec and so on. But tokenization is not a very difficult thing. Even though these days when you talk of large language models, okay, you're actually tokenizing with their tokenization is a bit more intelligent, right? And it is not always at word boundaries. So here you see that we use this counter class, which comes from built-in Python collection, right? A counter class is a class that allows you to count how many instances of anything that you have. So we create a simple tokenized function, which takes the text that you want to tokenize, splits it, right? And then so you create a counter, right? Then we pass the tokenized text into this counter. Okay, so what's happening here is each sentence is now tokenized, split into words, and then passed into the counter. Then we now start off with this index. So remember in the other one, we had a similar index here, right? Yeah, we have a little problem here. So yes, soft marks. So I need to remove the soft marks. I removed the soft marks in the, I should have removed it here. So I'll remove it here and then I'll rerun it. And I'll come back here. So we'll just continue from here and continue running. So yeah, so if you look at, we had the same word embeddings here. Let's see. Yeah, we had this word index. So it's basically the same word index that we are creating here, right? But we start off by indexing pad as 0 and indexing unknown as 1. So we have given these two the indexes or indices, pad and unknown. And for the remaining words, right, we now check for each of the words in this counter. By the way, let me show you what is in counter. Counter is a very useful data structure. Okay, so I've not run any of this yet. So let me run them. Let me run tokenize. So if I run counter now, so you can see what basically has happened is that each the number of times we've seen movies twice, right? But everything else is once. So that's what counter does. It's like a set, but unlike a set that will only allow a particular word to appear only once, the counter acts as a set, but it also counts the number of times if words are repeated, the number of times they appear. So we now take the counter and so for each of the word in this counter, right, we just use the length. So this is essentially generating it and it's using length of word to index. So it continues to incrementally increase the index. And then you now have an index to word, which is the opposite of the word to index. So essentially, you now have two lists. You have a word to index, and this is vocabulary size, which is the total length of the words. So if you look at this, there are 22. There are 20 words, one pad and one unknown. So that gives you 22. Now, if you can look at word to index, and you can look at index to word. So word to index maps the words to the indices, right? I is even there, which is the I. Then index to word maps the indices to the words. So this is the reverse. It's just a two-way lookup system. Okay. So then you now will create your embedding matrix like we did before. So we'll still create the embedding matrix. So like we did before, same thing. We specify embedding dimension. In this case now, we are using random numbers to initialize it. Scale is 0.6. The size is a vocabulary size and embedding dimension. So in this case, we do it. We do um, so the vocabulary size. Then the pad. Remember, zero is pad. So pad is always zero. So we make pad to be zeros, right? So by the time you look at this, right, you are going to get a matrix that always starts with zeros. Zeros means pad, then one means unknown. So any unknown character we will use this one. Then two and on will give you the embedding. But this embedding is a randomly generated embedding, not like what we used before. We used word to vec. Okay. Now, the next thing is we have to build what we call the next word data set, right? The next word is basically the next word which you will use for prediction. So, what this normally means is that it's like what I showed before, right? You will have a word like this, right? A single a single sentence. You will now build the next word, which is going to be a list that contains each word and the word that comes next, or each sequence of words and word that comes next. So this, right? And the word that comes next is movie. Then this movie, the word that comes next is was. This movie was, the word that comes next is fantastic, and so on, right? So this is basically all we just did in the other one. We'll now encapsulate it into a single class. So but we are creating a data set. So we're using PyTorch's built-in data set system. So the beauty of this is that once you create a data set, you can now create data loader from the data set. And then you can use your xtrain and xtest. So you don't need to do a lot of the things I was doing manually before, right? This will be automated. So if you look at this, right, it's kind of what I did before. You go through all the sentences. For each sentence, you tokenize. Then for each token, right, you get the index of each token, right? And if you don't find, you use one. Remember, one means unknown. So if I don't see, if you go back to our stuff, right, to our index, zero is pad, one is unknown. So what this is doing essentially is it is going through all the tokens, right? And for any token it finds, it will get it from the word to index, gets the index for it. If it does not find a token, it will use one. One means unknown. So we are going to get the IDs, right? Then we now create the context. So the context is you take the IDs, right? Um, the context is basically what we had here. Think of the context as the place where I'm going to slot in the words, whose the long words basically. So think of this as a context, right? The context will be all the zeros here. Then I pick the words that I need and I fit them in, and the remaining ones will remain as padding. Okay. So that's what's happening here. So we take a touch tensor and we just take all the IDs up to um up to the length, right? The I, because we are going from one to IDs. So we'll create a context, which is a touch tensor, and we take all the IDs up to that point, right? And that's what is a context. Then the target is the ID for this particular ID for this particular item, right? Or what we want to predict, essentially. In other words, the context is all the words before position I, like this one, this, or this movie, where I keeps changing. I goes from 1, 2, 3. You can see I starts from 1. So we start from the first word. So in the case of the first word, the context is all the words, basically all the words before the first word. And then the target is the first word, which is this one. Okay. But remember, we are using ID starting from 0. So when we start from 1, we are actually starting from the second word. So the context is going to contain this, and then the target is going to contain movie. Then when I increments to 2, the context is going to contain these two words, this and movie, right? And then as a list, the IDs actually, you can see it's the IDs, we are getting it from the IDs. And then the actual target will be the word that comes after that word, to which is was. So this happens that way, and we just append it. And you can see that the context and the target we are passing in as tuples. So the context is there and the target is there. And remember, this context is the variable length. It's variable length. It's not, we've not padded it yet. It's variable length. The padding will be done automatically by PyTorch. So we have the context and the target. So essentially, this is the training data. This is the X data, and this is the Y, what we want it to predict. Okay. Then so that's data set, basically. The initialization of data set contains all the samples, and we are doing it for each sentence, right? So for each sentence, we use all of the words to form the samples, and we'll now see the samples looking this way. The length of the data set is the length of the samples, right? Get item is to get any item at any particular sample. So let's run this so that I can show you what the data set will look like. I could actually just print something like data set, right, equals next word data set. So we'll put the sentences and we'll put the word to index. So that gives me the data set. Let's look at how this data set looks like now. Of course, you won't see it because, but you can access the samples which we created, and you'll see how the sample looks like. So you can see all the sentences have been spread out that way, where you have the first part of the sample is the index of the context, the words before it, and then the index of the word that comes after. So you can see all of that. So that's how that looks like. So after that, we now are going to create what we call a collate function. So a collate function is the function that would basically do all the padding, right? So you can see the key thing you see here in this collate function is path sequence. Path sequence is a function that PyTorch gives to us, right? From the RNN, utility module. It allows you to pad. So all that padding that I did manually here, right, where I had to run this, I basically did padding here, right, left padding. So path sequence will do that for you. So you don't need to do it manually yourself. So this is how you call it, right? So collate function is basically going to pull all the items in the batch, right? Which is going to give us all the context. So remember, when you load this batch, right, a batch is going to be made up of any set of this, which can be shuffled, right? You have generated sequences and you've generated, so this can be shuffled, right? And since you embedded it or wrapped it in the PyTorch dataset system, you can now use a PyTorch. This will be shuffled and any number that can be loaded as a batch. So when you take this batch, it's going to be made up of two components, item 0 and item 1. Item 0 will be the context, right? Which is this. And then item 1 is the value you want to predict, right? Which is the next in the list. Okay, so context is basically pulling only item 0 out of the batch. So only pulling this one for all of them in that batch. Then we now generate a torch tensor for it, right? But you can see that we are now generating the targets as torch tensor item 1. So basically I had done that. So the target is now this second part. So we generate target. Notice that the context is still a list. We have not turned into a tensor. We can't turn it into a tensor because touch does not allow you to use variable length, dimensions or sub dimensions, sub elements in a tensor. So we need to first of all pad it before we can convert it into a tensor. So, but we can convert this one into a tensor. So this is where we pad it. We pad it by using pad sequence, right? And we pass in the context. We specify that it's batch first, and then we specify the padding value, which is pad IDX. So remember, the padding value is the value we want to use as padding. In other words, to fill in. Here, I did it manually by just using values of zeros, which was a padding index. So if you paid attention, you notice that my padding index was 0. So I just use that value 0. You can use any other value. So that's why here, when you are calling pad, you tell touch what your padding index value is, which we should have defined earlier on. If we have not defined it earlier on, we are going to have trouble. So yeah, so you can see it's defined here as 0. So I can run this, right? The function has not run, it just exists. But the interesting thing is that right, padded context, when touch pads it, it's also going to turn into a tensor. So you don't need to turn into a tensor again. We can prove that by just looking at this data set that we have already created. I can say data set, you can pick the first element in the data set, right? Which just gives us this, or any random element. So let's say element 10, or we can even select a batch. So let's just select a batch from 10 to 15, right? So you can see that. Now, I take this and I can pass it through the collate function, right? So this collate function will be passed. This collate function we will not call it directly. So you can see collate function has now done the padding. This time around, you can see that it is doing right padding. I did left padding, but PyTorch is doing right padding because it is designed to work with right padding. So it does right padding. Maybe that's why my own training, it ended up predicting, um, oh, by the way, yeah, it ended up predicting it more than loved. Sorry, well, here you can see here it actually predicts love more than it, which is interesting. Okay, anyway, but the other time it predicted it gave it a higher logic, higher probability than it. But here you can see loved was it's pretty cool. Okay, so this does padding for you. So that's a collate function. So now that you've done that, you now create your data loader. Okay. So I've already created data sets. Okay. I already created a data set. So I'll just use that data set. Now, so the data set, you pass your data set into the data loader. You specify the batch size, how many items per batch. You specify that you should shuffle. You give a collate function. So this collate function is very important with the data loader. It's a generic function that you give any kind of pre-processing you want to do on the data before it goes into your model for training. You pass it, you implement it in the collate function. So you can see that our collate function takes the context, which we had already created, and then it converts them to touch tensor. By the way, your collate function should return the X values and the Y values as a tuple like this, and it should be as touch tensors so that it will be okay. So we are now using a data loader. So after a data loader, then um, the next thing is training loop. So this training loop will use a PyTorch. We'll use a PyTorch. Um, yeah, so we'll have the next word predictor, which we already have. Next word predictor. So I need to copy that from here. That's what we use. We already have a next word predictor, which I had created here. Okay. So Yeah, in order to run things really quick. So yeah, so this is the same thing that we had. No difference here, right? Even though our embedding matrix, we didn't use the word to vec, we just started from randomized. The interesting thing is that your model will actually learn its own embeddings. And these days, that's what it is. Yeah, so we can use CUDA if CUDA is available. We create a new model. We use our criterion, cross entropy loss. We use Adam optimizer. Epochs 200. You can see we don't need that many epochs, right? And we do the training. So in this case now, because we are doing batch loading, we use a loader. So we have another loop inside here where we are now loading in batches and training in batches. So we get the context from the loader. So remember, like I said, when you run the loader, it's going to give you a tuple, even though you could always make your loader do give the response in any shape that you want. Okay, so context target, you pass it into the device you want to use for training. You now run and get your logits, pass the context in, which is the X values basically. You get the criterion, which is logits and target. The logit is the same thing as Y preds, all right? And you get your loss function. You do your zero grad, you run your backwards, you do your optimizer step, and then you increase the total loss. So for batches, you can increase the total loss. Then when the epoch is done, you get your total loss. Um um I could also keep track of the losses if I want to. I always like to do that. Let's just keep track of all the losses, right? Um um okay, so we could also say average loss or mean loss. It's still zero. Then there are two ways you can track loss. You can track mean losses or you can track the actual losses. So when you are done with loading a particular thing, then we could just do mean loss. Yeah, so yeah, because yeah, well, I guess this can work. This can work. And then we run that. Okay. So that's your training loop. Simple, standard training loop. So we run the training loop. And after running a training loop, the next thing is you can then test the model and run. So you can see our epoch training has gotten better. By the way, last time my loss was very bad, but you can see the one I did myself, you can see the loss has gotten better, much better, simply because I removed the softmax. So the softmax was a problem. Softmax, when you are doing prediction, you have to append the softmax at the end, but don't use softmax when you are training, because the cross entropy loss also will use softmax. Okay, so now I define a function just to um, do the prediction. So I have to put this in a function because apart from doing the actual, we have to first of all take the text that I want to predict, okay, tokenize it, right? Then get the IDs from this, right? Then convert it to a touch tensor, pass it into the device, okay? And then, by the way, this version of tokenize also does the splitting. Um, just, just to show you, it splits, right? It splits and then it converts to tokens. So that's okay. So so I'm making a whole function to do the prediction, so I don't need to be doing each of these steps separately. So tokenize it, and then you get the IDs by going through the vocabulary list. You get the IDs. You convert the IDs to a tensor, right? and you put it into the device, and then you run it in inference, no grad. You pass it into a logics. You now get a prediction ID. The prediction ID is going to be the one with the highest value. Argmax, like I told you before, is going to give you which index has the highest values from this list here across this dimension. So it's going to give you which index. So you now take that index and you retrieve the word that comes out from it. And that's it. So this whole thing now gives you an entire function that you can pass in the words, right? And it will give you the prediction. So if I run this now, this movie was, you can see, fantastic. Just to prove that this works, right? You can try a bunch of other things. As long as it was in this your training data set, right? This movie was, it gave you fantastic because the loss is so good. It's basically overfitted on your training data. So if you can say absolutely terrible, let's see what that will give me. It will give you also very good. If I say absolutely terrible, okay. What's the next word? Film. Absolutely terrible film. It's able to predict that because you trained it. You can see it actually got it. Now, let me put a sequence that wasn't in our training data. Absolutely horrible. Well, the thing now is horrible won't work because horrible is not in our vocabulary, right? So you see what it does. Because it doesn't know horrible, it ignores horrible and just goes with absolutely. That's why it's giving you terrible, absolutely terrible. So this is one of the problems with this approach, a limited vocabulary. So if you want to train models to be better, you need to have a larger vocabulary, basically. So if I say absolutely film, right? Film is in the vocabulary, so it will come up with something. It still says terrible because it's basically overfitted around absolutely, right? So if you say fantastic, um, so let's go and see. You'll see that I probably comes after fantastic. So you can see, yes. So we have trained a model that has overfit on this data, right? That's what is going on. By the time you start giving it faster, fantastic movie ever. Now, let's see if the sequence of fantastic movie doesn't exist, but there's a sequence of movie and it comes up with ever. So this is kind of a very simple toy problem. Of course, this is far away from LLMs of today, where it's far more intelligent. But this is an idea of how we move from training models to just predict linear regression. We have actually moved from linear regression to actually predicting the next word in a sequence. So I'm going to end at this point because we've gone way beyond our time. But at least this gives us an idea of how this works. This same principle can be used for training on what we call sentiment analysis to say, okay, is this sentence positive or negative? I'm going to share with you the Jupyter notebook on that so that you can study on your own. We will not have time to go through it again. When we come in on Thursday, we are going to now talk about limitations of these sequence models. We're going to talk about sequence to sequence training, sequence to sequence model, the limitations, and how we solve those limitations with attention, what attention means, and how attention then evolved into transformers, which are the modern latest neural network models that we are currently using for the large language model, the GPTs, and so on. So I hope we enjoyed this class.